when two phases coexist, the temperature remains the same. So what we're doing here now is we're literally changing phases. Okay, so welcome to the last half or the last part of our chapter 14 lecture. So up until now, we've been talking about some basic definitions of heat and temperature. Particularly heat is the spontaneous transfer of, or heat is the spontaneous transfer of from one phase. Bring it up. There we go. So the latent heats. There's a few different. We have latent heat of fusion and latent heat of vaporization. The latent heat of fusion is the heat added or the heat needed to go from solid to a liquid, whereas for latent heat of vaporization, it's the heat needed to go from a liquid to a gas. The latent heat to convert from a solid directly to a gas is the latent heat of sublimation, and we don't have that shown on the chart here. We just have the latent heat of fusion and the latent heat of vaporization. I'm just going to move over now to this one. So the last slide that wasn't showing is basically the graphic shown here wasn't displaying. So what we can see here is, or what we should see on the other, is the latent heat of vaporization or latent heat of is going from B to C, and latent heat of fusion from A to B, and then sublimation would be from A over to D. So in looking at this problem here, we want to take a look at the heat transfer. We want to find out the mass of the block here. So so as the heat is first added to the ice starts out at -15. So we're adding a lot of heat. But notice that we have a really small positive slope going from A to B. So the little bit of heat's adding to bring about that temperature change. So it gets a temperature change up to 0, and that's when the ice starts melting. And no matter how much heat we add, look at that line, that melting line right there from B to C. No matter how much heat we add, that temperature still remains 0. And then once the ice gets all converted to water, then we go from C to D, and when we're adding the temperature, when we're adding the heat, we now see a corresponding temperature change from 0 to 15 degrees. So we're going to use our latent heat of fusion and latent heat of actually just our latent heat of fusion in this example. So when the heat is first added, it's when the block of ice, when we're at A. So the block of ice is at A. So that's -15 degrees. And then the ice melts, or the temperature actually goes up to 0, and then that's when you begin melting the ice block. And so the total heat is equal to the sum of the heat needed, or I'm sorry, back up a little bit. So we've got the block of ice melting, and we got the block of ice at A, and we get it to point B, and that's where it begins melting. So and then once it melts, the final temperature from C to D goes up to +15 degrees. So in order to find the mass, we're going to set the total heat equal to the sum of the heat needed to go from A to B, and then B to C, and then C to D. And so what we're saying there is we have this little drawing tool here, and our total heat is equal to the Q sub I plus Q sub II plus Q sub III. So the first one, Q sub I, is from A to B. So that's what this is right here. We'll put that, our Q sub I, right here. And then this one is Q2. And then this one right here is Q3. So if we look at Q sub I, I'm going to make that a little darker. So if we look at Q sub I, we could just plug our specific heat and latent heat equations right into the right into our equation 1. I'm going to label that number 1. So Q sub I, we have to solve for each Q right here, and then we'll solve for mass. So yeah, as you can see in equation 1, mass is not a part of it. So Q sub I, we're going to use the specific heat equation. We're not using the latent heat of fusion. So going from A to Q sub I is going from A to B. So we actually do see a temperature change. We see a temperature change as a result of the heat being added to the mass. And that's evidenced not only by the bar going from A to B, but we see that positive slope too. So we see the positive slope going from negative 15 to 0, and then we see a flat line from B to C. And the flat line is the latent heat of fusion that we'll use. So we're going to come down here and put our equation. So Q sub I is going to be the mass times the specific mass of the block of ice times the specific heat of ice, and that temperature change right there. And then the second part, going from B to C, is the latent heat of fusion. So that's just Q equals M times the latent heat of fusion. And then the last part from C to D is back to our specific heat again. And now we want the specific heat of water. And then we're, of course, looking at that temperature change right there. So when we rearrange our equation to solve for mass, we're going to wind up with the Q is in the top part, the numerator, and then down in the bottom is the specific heat of ice times the temperature change plus the latent heat of fusion plus the specific heat of water times that temperature change right there. So so our total Q, we know that that's let me try and move this up a bit here. So so our value of Q, we're given that, and that's our 9.5 times 10 to the 5th joules. And then we have our specific heat of ice. I'm going to leave off the units just for space sake, but know that the specific heat is joules per kilogram Celsius. And then we're going to multiply by our temperature change, the final temperature. So remember, we're going from A to B for this part, so the final temperature is 0 minus a negative 15. Plus latent heat of fusion of ice is 33.5 times 10 to the 4th. And then we're adding our specific heat of water and our temperature change. And the temperature change there is positive 15. That's your final minus your initial is 0. So our mass ends up being 2.2 kilograms for that one there. So one little demonstration of using latent heat, and another example is this one. So we have an initial temperature of 5 degrees, and we have if I hope you can see that. So in this one here, we have a block of ice, initially at a temperature -5. And then we know an amount of Q that's being added, 5.2 times 10 to the 5th. It says 10, that says 105 right there, but that should be 10 to the positive 5. So that amount of heat is added to the ice, so we want to know the final temperature. And how much ice remains. So we're making an assumption that ice actually remains here. Oh, sorry about that. I got a nasty cold, obviously. So our first thing we want to do here is the specified amount of height's being added, and the first thing we want to do is calculate the heat necessary to raise the ice to the melting point. So that's the specific heat. We're not changing phases yet. So remember that a latent heat or latent heat of fusion or a latent heat is changing from one phase to another. So as long as you're staying in the same phase, then you would use the specific heat. So we could draw our diagram here. Here, so this is our first part, and this is our second, and this is our third right here. So the first part, we're just the amount of heat is m times the specific heat of ice times that temperature change. So so we get let me erase our little drawing. You can refer to that from the other page, but basically what we're doing is we're still going up that step. So here now we can put our mass is 1.1 kilograms, and then the specific heat is 2090, and then our temperature difference is 5 degrees, 5 degrees Celsius. Or 5 Celsius degrees, we should say. And then, so that comes out to 1.15 times 10 to the 4, and that's in joules. And then our second, that's how big Q1. So our second here, the second amount is, now we're changing. Now we're on that flat line where we're changing from ice to water. So we need the latent heat of fusion is what we want to calculate here. So that's going to be our mass times our latent heat of fusion. And our mass is 1.1 kilograms. And that's multiplied by our latent heat of fusion. And this is right off our chart. And that's joules per kilogram. So we see where the kilograms cancel out right there. And we get a Q2. That's equal to 3.685 times 10 to the 5th joules. 10 to the 5th joules. And then our last one, now we're going up to, now we're going from melting up, it's converted to a liquid, and we're we're not changing phases, we're just heating it up. So for this one here, the Q3, in order to find that, we're going to just rearrange our first equation that was Q total is equal to the sum of 1, 2, and 3. So Q3 is equal to, consequently, the total Q minus Q from the first phase and Q from the second. So this one gives us our 5.2 times 10 to the 5th joules minus our 1.5 times 10 to the 4 minus our 3.685. So they're the two that we calculated already, and we find that Q3 is going to equal 1.40 times 10 to the 5th joules. And if we just move that up a little bit here, we could see, so you erase that part. So we could see here that, so see, were we required to find, oh, I'm sorry, we're not required to find the mass. We're required to find what factor the temperature changed. So when we want to look at the temperature final, the final temperature is in that last leg when so you melt at the heat and then you raise the temperature of the block of ice and then you melted it to water and then you heat it the water. So that last phase, that last line, the third Q, that's the one that we want to use to find the temperature difference. So the temperature difference again here is our M times our C time heat capacity of water times that temperature change, and that temperature change, of course, is T final minus initial, and the initial was 0. It had melted, the melting point there. So when we rearrange that equation, or this one here, I'm going to actually cross this off and put that as our T final minus our T initial. So that's a T. And then our equation for T final is Q3 divided by the mass and the specific heat of water. So that gives us a temperature of 30 degrees Celsius. And so if we have a final temperature of 30 degrees Celsius, what do you think that tells you? So basically what it tells us is that no ice remained. We had made the assumption it says how much ice remains in that one question. Well, no ice remains, because if the final temperature is 30 degrees Celsius, that's greater than 0 degrees Celsius. So the amount of ice was completely the block of ice was completely melted. And then if the amount of heat added is doubled, then the mass of the ice must also be doubled in order to keep the same temperatures, in order to keep the same final temperature. So you would also need a bigger block of ice than if you were to do that. So next slide here, and this one here is number 62. So I hope you can read that there. It's a little hard for me to see, but so here in this problem here, the figure below, this figure right here, is temperature versus heat plot, and it's for 1 kilogram of water. So it's basically showing us the process of where we have ice from up to point A, from our origin to point A is ice, and then from A to B we're melting, and then B to C we're heating the water, and then C to D it's giving off as steam. So here in A, actually this one we're just going to start from A. So it's asking us calculate the heat corresponding to points A, B, C, and D, and then calculate the slope of the line. So at A, heat's added, and it's heat's already added, and but we're actually just going to use the specific heat here, and so we wind up with a Q. Oh, sorry. We have a Q sub A, and that's equal to our mass, and then our specific heat, and that's going to be of ice, and then our change in temperature. So the mass is 1 kilogram, 1 kilogram of water, 1 kilogram. And then our specific heat of water is 2090, and then our temperature change is 20 degrees. We went from negative 20 up to 0. So final is 0, and then the initial is negative 20. So final minus a negative gives us 0 minus a negative 20 gives us a positive 20 there. And so Q sub A is equal to 4.18 times 10 to the fourth joules. And then when we add the heat needed to melt the ice, so going from A to B is that phase change. We're melting the ice to water, so it's a phase change, and consequently we need to include the latent heat. And but it's not just the one latent heat; it's also the it's also the specific heat. We got to add the latent heat to that specific heat over here for the total amount of energy or heat at that spot. So we want to calculate the heat corresponding to A, B, C, and D, and so we have our Q sub B is equal to here our Q sub B is equal to the heat added. So it's Q sub A plus the latent heat of fusion. So Q sub A is what we calculated before. And that's 4.18. times 10 to the 4 joules, plus the latent heat of fusion for water is 4.18 times 10 to the 4th. And again, that's in joules. I'm sorry, I would back up. I made a mistake there. So that's not our latent heat. That's the specific heat we just calculated. So we have our heat that we just calculated, and then our mass of 1.1, and then our 1 is just 1 kilogram. 1. And then it's going to be times the latent heat of fusion for water is 33.5 times 10 to the 4th. And again, this Q up here, write that a little meter. So that Q sub A is our 4.18 times 10 to the 4 joules. So down here for Q sub B, when we multiply all that out, we get 3.77 times 10 to the 5th joules. And then Q sub C is this part, is right here. So we're adding heat, and we needed to raise the temperature to boiling point. And then, so it's a similar thing here. It's our Q sub B. We start out Q sub B plus the latent heat of, or I'm sorry, not the latent heat, the specific heat of water, and specific heat of water times that temperature change. So what we get there is our Q sub B is our 3.77 times 10 to the 5th, plus the mass of 1, and then the specific heat is 4186, and the temperature changed 100 degrees. So Q sub C is Q sub C is equal to 7.96 times 10 to the 5th joules. And then when we add heat to boil off the water, so move this up a little bit. So add heat to boil off the water, you get at Q sub D, you wind up with 7.96 times 10 to the 5th. That's the Q sub 6 that we just calculated, and plus the latent heat of vaporization. Let me write that later. That's latent heat of vaporization. So latent heat is mass times, or specific heat mass times, latent heat of vaporization. The equation is Q, the amount of heat transferred, is M times LV. And when we substitute everything in for that, we get equal to 3.06 times 10 to the 6 joules. And then to calculate the slope, slope is rise over run. We can't get this to move. But if we took a look at that, so the slope again is T sub C minus T sub B, as we went from B to C. So C is the final minus the initial. It's Q sub C minus Q sub B, and it equals 100 degrees Celsius. I'm sorry, Celsius degrees. That should be 10 degrees. And yeah, I'm sorry, that's 10 degrees. Or no, I'm sorry, 100. That is 100 degrees. And that's in Celsius degrees because it was a temperature change. And then our Q sub C minus Q sub B is 4.186 times 10 to the 5th. And we wind up with the slope being the slope is the slope equals 2.39 times 10 to the negative 4. And then you can also calculate that by 1 over the specific heat of water. And both of them come out to be 2.39 times 10 to the negative 4. So that brings us to our next. So in that latent heat section, we were addressing adding or removing small amounts of heat to and from a system. And so this, or actually a little bit before we move on, I know it's kind of hard to see that handwriting there. So, I don't have the slide, I don't have the solutions posted yet. I need to get to a scanner to scan them in. But in the meantime, try and solve those problems, and we'll go through them again on Monday, during Monday's class. So in the latent heat section, we addressed adding or removing a small amount of heat to or from a system. So this section addresses heat exchange within the system because it's parts, but not within a system between the parts of that system. So the external world we're ignoring. And we'll see that the total energy is going to be constant or conserved, although the heat flows within the system can cause changes in temperature and changes in phases. So in solving the energy or solving conservation problems, you would set the heat lost by one part equal to the magnitude of the heat gained by another. And we're not really going to get into conservation too much here. We did that a lot last semester. But more importantly, is setting the foundation for moving into the our discussion of internal energy, which is on the next chapter. So move forward through here, and we see these are all just summary slides. If you have any questions, please, of course, feel free to email me, and I'll post these on Canvas now. And